MODPIE is a toolset designed to help system experts pose performance questions and decide on the optimal architecture for a software execution model, or SEM. We will be executing an existing model of an unmanned aerial vehicle, or UAV, to demonstrate the functionality of MODPIE. MODPIE is broken up into 4 phases: the modelling phase, the deployment phase, the execution phase, and the observation phase. Each phase has its own unique tool. The Generic Modelling Environment, or GME, is an off-the-shelf and open-source modelling tool which supports many modelling languages. In GME, the system expert constructs a model-based representation of the distributed real-time system. For each software component in the system, a component interface is constructed. For the UAV model, there is a GPS, controller, and comms component. Each component contains a set of input and output event ports and a corresponding behavioural model. This information is modelled in accordance with provided documentation and specifications of the system. The behavioural model is where the business logic is implemented by the system. Each component has its own unique behavioural model, and each input event port in a component interface can have its own series of events attached to it. This chain of events is executed every time that a particular event port receives a message. The message which triggered an event can also be logged. Actions can be used to utilize CPU resources, allocate memory, and also send new messages through the output event ports. Branch statements and state variables can be used for more complicated business logic. Once each component is modelled, the system expert then creates an assembly for the system, creating implementations of the component interfaces and connecting the input and output event ports together to form a system of components. Once the assembly is complete, the system expert is able to export the SEM. The second phase is deployment. The deployment generator tool is designed to produce a deployment configuration which describes how the SEM is to be deployed on a particular hardware testbed. The system expert chooses which middleware this software system will use to form the connections between components. The SEM file is then imported, extracting all of the software components from the assembly of the SEM into the deployment generator tool. The system expert imports the list of hardware nodes. The test bed of hardware nodes are physical or virtual machines, which are running an array of different operating systems, architecture, and hardware, ranging from powerful multi-CPU servers to lightweight ARM machines. Once the components and nodes are loaded in, the system expert is able to select and connect the components and nodes together. The system expert may have to deploy software components from the model onto a specific node to adhere to non-functional requirements provided. Along with the SEM, the deployment configuration file is put into version control and used by the execution phase. The third phase is execution. Jenkins is an extendable open-source continuous integration server. It has been configured and scripted to manage the hardware nodes which make up the testbed, and controls and automates the distribution, compilation, and analysis of the execution of the SEM. It is a framework which provides reliable execution and repeatability. The system expert executes the build job and provides the Jenkins system with a URL to the version controlled model. A duration is also provided for the length of the experiment. The Jenkins infrastructure automatically generates the C++ code for the SEM for the targeted nodes and middlewares and remotely distributes this code. The code is then built on the hardware nodes and executed concurrently. Once the execution has completed, analysis of the resulting database of log messages will be executed. This analysis can provide insight into the performance of the SEM on that particular deployment configuration. The final phase is observation. The visualization tool has been developed to run on a Microsoft PixelSense table. It runs concurrently with the execution and provides real-time visualization of the SEM and underlying hardware testbed. It is able to monitor the network traffic, CPU and RAM utilization of each hardware node and software component involved in the deployment. Bottlenecks and hotspots can also be visualized. The tool helps to provide a visual insight of the performance of the SEM and helps to identify potential improvements for future iterations of the model. Through the use of the MODPIE toolset, the system expert is able to model, execute, deploy, and analyze the model, providing early insight into architectural characteristics and assisting in the design and future development of the model.